Okay, so if I had that, how am I finding the inverse function? Good. Right, excellent. So what we're doing is just rearranging this. We're swapping x and y, and then we're rearranging to get x by itself. Sorry, y by itself. Sorry? Okay, that's what I'm going to try and show you. All right, are we watching? So if this is our function, right? So f of x is this. Remember, so our inverse function is this, right? Does anyone remember what that practically means? If we're just swapping x and y, what does that actually mean? Neither. Okay, so you're right about the line of symmetry is what? Yeah, what is the line of symmetry? Y equals x, right? So the line of symmetry is y equals x, right? So if we're graphing, it's this. So that is our mirror line. And so whatever the graph looks like, our graph flips this, because what we're doing is we're flipping the x and y coordinates of every part of the graph, aren't we? Right? And so that is what it's going to look like. So let me sharing your screen. Yeah, okay, I'll do that. I'm going to share my desktop. And I'm going to go to Desmos. And I'm going to not use that one. Actually, no, maybe I will use that one and I'll just turn this on. Okay, so if I have what, let's say that I had, what was my equation? Y equals what? I can't even remember what it was. Forget. 3x plus 4 all over 2. Okay, so that's what it would look like. So then what was my inverse graph? 2x minus 4, good, all over 3. See, okay, this is, I really don't want to change the, this is very difficult. Oh, yeah, but the problem is I don't want to zoom in because I have it perfectly set for what I want to show you later. But this, if you saw, this actually flips the graph of y equals x. It's just very badly done right now. Okay, that's annoying, isn't it? All right, I'm going to get rid of those two things. Okay, so what I would like to remind you is of our, so we are going to do inverse graphs of our trig graphs, okay? So what did we just say? What we're actually doing is flipping all of the x and y coordinates. All of the x and y values are being swapped when we do inverse graphs. So I want you to try and predict what is a sine wave going to look like when we flip it. Okay, so you think it's going to be like a wavy thing like this? Okay, is that going to be exactly what happens? It's a little more complicated than that. You're on the right track. It certainly is going to be wavy in the other direction, but can you maybe make another prediction about what might happen here? Okay, there's a different prediction. So think about, this is actually, remember, this is a unit circle that is put into waveform. So if we flip everything, what we're actually doing is limiting what we can go up to or down to, right? We have limitations on how far we can go. So if I show you the sine wave, it actually only goes from -90 to +90. We get stuck, right? It only does one little bit of this curve. The domain restrictions and the range restrictions mean that it does not keep going as a wave. And we will see more of why when we actually draw stuff and try and calculate it. So if you're thinking of a unit circle, you really can't go any further of a sine wave without ending up in incorrect quadrants and things that don't make sense.
Is that because like this is all right angle triangles? So an angle can't be doing.
Not necessarily right angled triangles, it's all with triangles though. So I want you to think about the sine ratio. Sine is what? Opposite over hypotenuse. Is it possible that this value is ever bigger than 1? Why not? Right. So because the hypotenuse is always the biggest side length, this number on the top must always be less than that, which means the fraction is always under 1. Is that true with cosine? Yeah, it is, right? So we still have the hypotenuse involved. What about tan? Right. So tan can actually be more than 1 because we don't know which one of these is longer. It's okay for either of them to be longer, but it's not possible for these ones, which is one of the reasons why we end up with particular restrictions when we're talking about sine and cosine. All right, I'm just going to delete this so I can use my graph again. All right, so what if, I'm going to stop annotating. Oh, I didn't mean to do that. Okay. All right, so the cosine wave, can anyone predict how it's going to be different? It might go the other way. Any other predictions you want to make? Ah, very good. Why is it going to shift up? Because cosine actually starts in a different place, doesn't it? So you're right that it flips, but it actually also starts at 1, and this one goes up to 180. So remember when we did this version, right? So sine is there, but cosine starts here. So instead of starting at 0, we start at 1, and our inverse reflects the same idea. This one goes through 0. We've still got 0, 0, but this one, we do not have a 0, 0. This one here goes through at 90, all right, which is halfway between 0 and 180. All right, we know that our tan, I didn't mean to show you that one first. Our tan graph looks like this. Again, we are going to push this one sideways and we get like a weird long loop thing here. What do you think the asymptotes might be here? 90, right? Look at this. This is going to approach 90 and never hit it, and approach negative 90 and never hit it. Just like this one here is doing that. So this is also going to approach 90, and this one is also going to approach 270. This one is going to do that in the same direction. So this one, remember, every 180 degrees, the tan wave repeats. It's the same thing on its side, right? We go up 90 and down 90, so it's 180 as well. All right, so what we want to do is think about, oh, actually, there was one more thing I wanted to remind you about. I'm going to stop sharing that for a second. Let's go back to our digital whiteboard. I want to remind you about something about inverses as well. So if I multiply anything by its reciprocal, what on earth just happened? Okay, my laptop had a breakdown yesterday during Zoom had a total breakdown yesterday during grade 10 maths. That looks like it's possible that it's going to do that again today. Okay, we'll do that. So 3 times 1/3 is 1. Okay, this is really weird. 5 times 1/5 is 1. Oh my gosh. Okay. 2/3 times 3/2 is 1. And that means that x times 1/x is 1, which doesn't actually fit on the page. Okay, so if I said anything, this is one of the rules we talked about last year. Okay, so anything multiplied by its inverse, I don't even know where it is anymore, is 1. Okay, it's not quite 1 though, is it? What was it? It's just back to its original thing, right? It's actually x. See if I can write it there. Okay. Let's guess. Hey! Okay, so anything multiplied, so any function multiplied by its inverse, everything's going to cancel out to x. The same is going to be true of a trig function. So, I wonder if I can just close this. Can I just stop sharing and then see if it starts again? Oh gosh, new. Let's just see if it lets me do it this time. All right, so any sine thing multiplied by its inverse is also, geez, So if I have sine of, oh, sorry. If I have sine 30, if I can write that closer, sine 30, sine 30 times okay, what do you think is going to happen here? Okay, they're all just, okay, so they're all basically canceling out to nothing. So if I have, oh, actually, I'm writing it wrong because I can't actually write it. This is so annoying. So if I wrote, I'm just going to try and write it all here. So if I wrote something like, oh, okay, if I wrote something like that, the answer is just going to be that, right? Because these two bits are essentially canceling each other out, just like any other inverse would. Now, you very much need that little table I made you draw the other day. Remember where we had 30, 45, and 60, and then we had radians, sine, cos, and tan. Let's see if I can zoom out and find that. Remember I made you make a table like this? Okay, so get that back out because you're going to want to read it today. So you're trying to find exact values. If you've got, gosh, here we go. If you've got sine of inverse sine of, let me find an exact value. I've lost my spot. Of half. Okay, so if I had that, what would, oh, with an extra bracket on the end, which I can't draw, what would the answer to this be? 30, right? So this should be 30. So we're trying to read our graphs. Okay, most of it is that today, remembering that all, you can also read things off your actual sine waves if that's going to be helpful. But I think just using the table will be enough, but you should be able to do it either reading it off the graphs or reading it off your exact value table. Okay, let's have a go. Exercise 5.3. I would like, okay, I just quickly want to tell you that I'm changing something. On your timetable, it tells you to do specific questions. I actually want you to do the whole thing. It won't take long. You're just reading things off a table and I just want us to practice that. So yeah, please do the whole of the exercise. 5.3. All right, great.